Good day, everyone. We're reviewing Wetzel's Limnology textbook. This is edition number 4, and we're in chapter 8, which deals with water movements. And more specifically today, we'll be looking at exchanges at boundaries. The hyporheic zone. So the hyporheic zone, because they're not defining this in the text, is the zone just below a stream. So it's the pore space of the sediment and the cobbles and the gravel below a stream or river, or underlies the stream bed where surface water overlies permeable sediments. The saturated area has interstitial spaces that enable exchange between the relatively slow-moving groundwater and the stream itself, and additionally hosts communities of microbes and benthic invertebrates. A two-way exchange occurs between the stream and hyporheic zone over small scales, centimeters to tens of meters, which distinguishes it from groundwater, which has unidirectional travel, discharge or recharge over extended areas. So let's look at figure 8-19 here. Schematic of the hyporheic zone and the downwelling and upwellings that enable exchange between a stream and its adjacent hyporheic zone. Groundwater flows into the hyporheic zone and then into the stream. Dark blue denotes surface view, and pale blue indicates cross-section. So this is superficial, this is cross-section. This is the hyporheic zone. This is pretty much the gravel below the stream. This is the stream, and the water is moving from left to right. And then groundwater is below the hyporheic zone and is, for example, in here, because the stream is at an angle. I mean, the slope is at an angle here. The stream is gaining, so there's groundwater that is moving from the aquifer into the hyporheic zone, ultimately very likely into the stream. And then here it's the reverse, according to those little arrows, although they may be in both directions, where the groundwater is feeding the hyporheic zone or vice versa. So bed form driven exchange. So this is between the stream and the stream bed. This is the hyporheic zone, as we were saying, and then the main stream channel. Exchange between the stream and the hyporheic zone is mediated by the morphometry of the stream bed, which creates water level fluctuations and drives vertical hydraulic gradients across and along the stream bed, resulting in localized areas of the stream that may gain or lose water from hyporheic exchanges. The gains, upwellings to the streams are from small decreases in the hydraulic head, and the losses, downwellings, from increases. Most of the water in the hyporheic zone is derived from the stream channel, about 98% at the top of the zone, and 10 to 98% in the interactive zone that intersects with groundwater at its lower and lateral boundaries. So it's quite the margin between 10 and 98%. Changes in the topography of the stream bed contribute to variations in exchange with the hyporheic zone. Stream water typically enters the hyporheic zone in areas where water pools above boulders or bed constriction, as well as where there are small-scale hydraulic gradients like riffles. Water returns from the hyporheic zone to the stream, mostly in downstream areas, as the slope of the stream bed decreases and pools predominate in the stream reaches. Exchanges are also mediated by the permeability of the sediments, stream sinuosity, and length scale of roughness features that is presence of rocks and boulders. Approaches to modeling the exchanges are described by Mazardri and et al. D. River and stream morphology, currents and sediment loads. Flow velocity and distribution in rivers and streams depend on the extent of curvature. Flow in straight section of the main channel is parabolic, with the highest velocities near the center and lower velocities near the margins due to friction. As the channel curves, flow accelerates at the outer margin of the curve and decelerates on the inner margin. The changes in stream flow additionally lead to changes in cross-stream flow, which lead to surface waters exchanging with bottom waters. High discharge affects stream morphology and sediment load. During high flows, strong shear forces are generated, which affect the form of a stream channel and the suspended sediment load entrained in the bulk water of the channel. The increased load of suspended material is maintained in the water column by turbulent eddies. Suspended load concentrations are relatively uniform in the bulk stream channel above the sediment water boundary layer, making measurements straightforward using grab samples, although an integrated water column sample is preferable, but with a caveat that large variations occur on the rising and falling limbs of a hydrograph, when high-frequency sampling should be used to estimate sediment loads. The rising limb of the hydrograph is usually characterized by higher sediment loads than the falling limb because fine particles are initially washed into the stream and entrained within the channel, but their supply is gradually depleted over the duration of a major storm event. Suspended loads can be quantified using turbidity as a surrogate measure, usually reported in nephelometric turbidity units or NTU. The relation of turbidity to suspended sediment concentrations varies with the size, shape, and refractive index of the suspended material. Suspended material includes organic and colloidal particles as well as inorganic suspended sediments. The total stream suspended load also includes bed load, that is, sediments that move along the stream bed in close proximity to it. Sediment traps and tracer studies can be used to approximate bed loads. These are usually smaller than suspended loads but increase substantially during flood periods. Rivers generally migrate across floodplains gradually, but sometimes changes occur abruptly. Such changes are called avulsions and nourish the floodplains with water, sediment, and nutrients, but may also cause drastic flooding. Avulsions can occur, for example, when, after several years of drought, sediment particles that have deposited where river waters flow are abruptly scoured during flood events, leading to changes in the river's flow path. Widespread alteration of stream flow by humans, for example, through abstraction, damming, wetland drainage, and other changes, has led to the recognition of the importance of environmental factor flows, E-flows, that seek to return the hydrologic regime of the stream toward its natural state and provide benefits for nature and humans. So let's look at 816 here. So variation in flow velocity along the channel of the Spree River in Germany due to curvature and B secondary currents in the river's cross-section at location 6,6, with depth enlarged 5 times relative to breadth. LB and RB refers to left bank and right bank, respectively. Okay. So A is we have pretty much like transect of the changes in the velocity of the water across these transects, so from 1 through 7, and 6 represents the transect 6 is represented here in B. So what we see is we have lower velocity along the edge of the stream or the river, and we have higher velocity in the middle, like as we're talking about it in the text. And that is because there's friction between the water and the edge of the bank of the rivers here, where there's no friction in the middle of it. And then this is the left bank and the right bank. So this is left bank here and right bank here. So we're looking from here to here. So from here to here. So these are stations, 9, 8, 7, I believe. And so that shows, so the length of the arrow shows the magnitude of the velocity, and then the direction of the arrow shows the direction of that specific water particle. So here what we see is at the left bank we have like these vectors that are showing velocities away from the bank itself, and then in the middle of the stream we have actually slower velocities, and then here at the right bank we have the same phenomenon where we have like the arrows pointing away from the bank itself. At the bottom of the of the rivers. So the rivers, as you can see, is not straight, like it has a diagonal to it. It's shallower on the right bank than it is on the left bank. We have the water tending to move from the left bank to the right bank at the bottom of the rivers. And so what is interesting here is that the left bank here has pretty good velocities, even in comparison to the middle, which is not the case, for example, for station 2, where we have slower velocities right at the edge of the bank compared to the middle of the river. And that may be due because of the fact that the water is colliding with that edge here, and is accelerating in that area here. And where we have a tendency actually for scour in this area here, for erosion and then deposition in this area here, which can create what are called oxbow lakes right here. All right, so water movements 3, water movements in lakes. Lakes are in motion from wind on the water surface that transfers energy and momentum, heat loss that induces instabilities, and convectively induced motion, rotational effects of the Earth rotation, and intrusion from stream and rivers. The energetics of various processes are illustrated in figure 8-6. Wind induces motions at the surface, including currents, surface waves, surface seiches. So a seiche is where you have water movement for an entire lake. And so kind of like if you were in a bathtub and you created a wave in the bathtub, and then the wave would propagate from one edge of the bathtub to the other edge. So it's kind of a lake-wide movement. We're probably going to look at that in a minute. Meyer cells and gyres. An approximation of energy transfer from wind is given by Imboden 2003, which indicates that 20% of the wind energy input at 10 meters above the water surface is transferred into surface waves, and an even smaller fraction into currents, seiches, and turbulence. Wind causes the thermocline to tilt, which induces internal waves such as seiches or non-linear waves that cause mixing. Flows from differential heating and cooling are common, reinforced by the complexity of basin morphometry and the presence of plants that can shade the water. Basin size and shape, as well as the prevailing energetic forcing, critically influence the period, intensity, and location of basin scale water movements. So, wind-driven motion near the surface. The movement of surface water is strongly influenced by the strength, duration, and direction of wind. So let's look at figure 8-17. Lake Dunstan, foreground with wind-induced surface wave, some of which are white capping and incoming Clutha River, and this is in New Zealand, in the background. So this is the river, and this is the lake. And mixing zone, this is the mixing zone, where the rivers enter the lake are apparent as changes in colors as is carrying along the river margin, indicated by increased turbidity, which will transport sediment into the lake. So you can see there's scouring here. This is, I think, what they're referring to. So it's kind of an interesting color. It's kind of purplish. Anyway, figure 8-18, wind rose on Lake Mendota in Wisconsin due to Langmuir circulation in the surface mixed layer. The wind rose a line roughly parallel to wind direction and the direction of wave propagation. Foam and light organic matter accumulate at the convergence zones, making the wind rose, also known as streaks visible. So these are the wind rose. This is white capping, and so there's foam accumulating there as well as organic matter, although we cannot really see it very well. And so that's pretty much like driven by the winds, and so you can therefore infer that the wind is coming from the person taking the picture toward the horizon here, I believe. All right, so equation and theory for these processes are summarized in McIntyre, when wind, Mooney-Smith and McIntyre, when wind blows over a calm glassy lake, it generates shear, which results in surface currents moving in the direction of the wind at approximately 3% of the wind speed. Due to friction, currents decrease with depth from the surface downward. When the upper mixed layer is not heating or cooling, a velocity profile follows the law of the wall scaling, presented in equation 8-4. A similar expression describes velocity with height above the water surface with u star a prime, the air friction velocity. Shear stress on the water surface tau is the product of the density and the friction velocity squared, and is assumed equivalent on both sides of the air-water interface. So here's the equation, and I'll let you review that. Many lakes are sheltered by trees or hills, which affect the wind field, while there is also a lag time for lakes to respond to the prevailing wind forcing. Okay, so then we talk about these authors. In fact, the flow consists of turbulent eddies. In larger lakes, wind accelerates as it flows over water distances of about a kilometer. Wind can also vary, especially over large lakes. So this is gyres in Lake Tahoe, California, detected using remote sensing. Current vectors are black arrows. Scale is in the upper left, and colors indicate temperature anomalies. That is the difference in temperature relative to the mean value. Okay, so this was taken at a point x in time, and this is north, and this is south, west, and east, and the arrows show the velocity, and then the length of the arrow shows the velocity, and then the head of the arrow shows the direction of any specific parcel of water, and then the color shows the temperature anomaly from the average. So, for example, we can see that on the east shore, Lake Tahoe, we have a high temperature anomaly, and where, like on the northeast side of Lake Tahoe, we actually have a negative temperature anomaly, and then even like here, we have quite a negative anomaly over here on the west side. And so this is probably a gyre right there, and that is illustrated. And there might be one that was trying to form right here. All right. The upper mixed layer undergoes a cycle of heating and cooling during the day. Unless conditions are exceptionally windy, it is divided into an actively mixing layer, a diurnal thermocline, and subsurface layer. The diurnal thermocline, which sometimes reaches the surface, and the subsurface layer are stratified. At night, due to cooling, stratification is eroded, often to the depth of the seasonal thermocline. Shear in the upper mixed layer varies with the extent of cooling and heating, and can be quantified with the Monin-Ukloff similarity theory. So we already went through that in chapter 7, so it's just pretty much the same stuff. So as wind speed increases about 3 meters per second, small erratic surface deformation known as capillary waves form that exceed the resisting force of surface water tension. As wind speeds continue to increase, surface gravity waves form. So water is displaced upward and returned to equilibrium by gravity along a circular path. Therefore, the waves are called gravity waves. They are coherent, though not uniform, and characterized by their wave period T, wavelength L, and significant wave height HS. HS is commonly denoted by the average height measured from trough to crest of the highest one-third of the waves. Due to the various controls on HS, including fetch limitation, empirical equations have been developed to characterize it and other characteristics of surface waves. As surface waves travel, they are called progressive waves. As they enter shallower water, their velocity decreases proportionally to the square root of depth. A reduction in wavelength occurs with a marked increase in wave height, such that the waves become asymmetrical and are unstable and break. In a plunging breaker, the forward face of the wave becomes convex and the crest curls over and collapses, whereas the crest of a spilling breaker collapses forward, spilling water downward over the front of the wave. Wind speed, fetch, and depth affect the evolution of surface waves across a lake, with waves usually limited by fetch at the windward end and depth at the leeward end. While whitecapping and breaking occur offshore as winds exceed between 6 and 8 meters per second, and wave breaking inshore can be accompanied by near-bottom shear. This transition from deep to shallow water waves occurs where the water depth Z is less than approximately 1/2 of the wavelength. D is less than 0.5 L. At this point, the idealized exponentially decreasing orbital motions of deep water waves become elliptical and flattened, generating shear at the boundary from the oscillatory motion of the waves. The shear stress can resuspend sediments and mobilize nutrients and metals, and resuspend fine sediment can be transported by currents to deeper areas. High sustained winds from one direction can lead to storm surges, exposing bottom sediments at the windward end of the lake and piling up water at the leeward end. For example, Hamblin recorded a 4.5 difference in water level between two ends of Lake Erie during a storm when wind direction was aligned with the longest axis of the lake. So I think that's going to be it for today, and we'll start again tomorrow, and we'll be looking at surface stages. And thank you for your attention, and looking forward to meeting you tomorrow. And take it easy and have a good day. Bye.